Okay, folks. If it's time for class to start, you know you want to have a clean sheet of paper. Okay? Okay, clean sheet of paper, folks. As I warned you, you're going to see a lot of quizzes between now and the end of the course. All right? But this quiz that you have today is going to have an interesting ending. The quiz is, folks, okay, want to put away your stuff in that? The Black-Scholes equation is the partial of v with respect to t plus 1/2 sigma squared s squared, the second partial of v with respect to s plus r s partial of v with respect to s minus r v equals 0. That's the Black-Scholes equation. Has variable coefficients. That's enough. Make a change of variables. So it has constant coefficients. Okay, go ahead. This was, as you know, one of the assigned problems for today. Pardon? You want to find a change of variables, yes. You want to find a change of variables. So what happens is, I wrote down the Black-Scholes equation, and I say it has a variable coefficients. Make a change of variables so that the resulting equation has only constant coefficients. And this is the last problem, I believe it was, on your homework for today.
What's the last part of the equation?
Minus RV. So the partial of v with respect to t plus 1/2 sigma squared s squared, second partial of v with respect to s, plus r s partial of v with respect to s minus rv equals 0. Has variable coefficients, s squared and s. Get the s out of there by making a change of variables, making it a constant coefficient problem. Okay, this is the problem I had planned to give as a quiz today. I wrote it down as a quiz today. I had 3 people ask me before class to give them some more insight into it. So I said, I'll show you what the quiz problem was to be today, and I won't collect it. And the TA is very happy. I won't collect it, but what I will do is go through it because it's important for you to know how to do this. You will see this problem again. So, let's get started. What I need to do is I need a change of variables. Okay, folks. Folks, I know you're celebrating, and I know you're celebrating that it's going to be 80 today. That's for the video because there's people outside outside of Irvine that are watching these videos, as I discovered, and let's let them know how we suffer here. You know, I mean, they're enjoying this 30-degree weather and or zero, but we need a change of variables, and the change of variables is to get rid of the s. To get rid of the s in s partial of v with respect to s. And again, we're not exactly sure what that should be. So what we do is we say, let magic happen. So I'm going to try to find x equals u of s, a change of variables, to get the s out of there. So with the change of variables, the partial of v with respect to s is going to be the partial of v with respect to x times the derivative of x with respect to s. Or the derivative of u with respect to s, the same thing. I'm free to choose that. I haven't told you what u is. You're to select u. So you don't know what u is. And so what is happening is we want to choose something to make our life easy. And what is the goal? The goal is to replace this by something that'll get the s out of there. Well, a way to do that is to let dus ds equal 1 over s. So I'm defining it to make life easy. When I do that, what I have here then is that s, the partial of v with respect to s, will equal s times 1 over s, that's going to be this term right here, times the partial of v with respect to x, which is equal to the partial of v with respect to x. And what we know from this, we now know the magical choice of u. U is going to equal the natural log of s. Now I know in certain of your courses they say when you see this, memorize this equation and stick it in there. Memory, it should be for important things like our basketball team is #1 in the Big West this week, etc. Those are important things. Here, you should know how to derive what are the change of variables. That'll help you in a large number of other settings. Now what we have is I've gotten rid of the s in this term. I've got to get rid of the s in this term. So, find the second partial of v with respect to s. That is going to equal the partial of v with respect to s. Wait a minute, excuse me, the partial of v with respect to s. But we have another name for that. The other name I have for that is partial with respect to s of 1 over s, the partial of v with respect to x. This is the product rule. So with the product rule, I have that it is the derivative of the first times the second plus the second times the derivative of the first. So this is going to equal minus 1 over s squared the partial of v with respect to x plus 1 over s, the partial of v with respect to s of, the partial of v with respect to x. And this is a part right here where a couple of people had difficulties to get the next step. So I want to show that for you. Any questions up to here? Yeah?
Could we have left the x's as s's?
S's is x's? We'll see. I'll look at your paper later. Okay. If you get the right answer, yeah. Okay. So now what I have to do is, darn, I don't know how to do this. I don't know how to do this. That's where the problem crops up. I think that's what you're asking. Okay. So how do I do this? Well, I got to get the s out of there. And I know that the partial with respect to s is going to be the partial with respect to x of the partial of v with respect to x by the chain rule times the partial of u with respect to s by the chain rule. Or excuse me, the derivative of u with respect to s. Just using the chain rule again. That's all I'm doing. And now what happens is we know what this is equal to. This is equal to 1 over s. So this is equal to minus 1 over s squared, the partial of v with respect to x, plus 1 over s. This is 1 over s times 1 over s is 1 over s squared, the second partial of v with respect to x. Okay. Everybody with me on that? Okay. Yeah.
Should the last one be du ds be dx ds?
The last one, because what I'm doing here is I have the partial with respect to s, and we know that the partial with respect to s is the partial with respect to x times the derivative of x with respect to s by the chain rule. Because x only depends on s. And so it's a derivative rather than a partial. And so that's where we have that. And I'm just using the chain rule right there. Good question. Okay. Any other questions? Yeah.
Where's the du come from?
Magic. What I'm trying to do is find a u. I'm trying to find a u.
I mean, on this board, the very last ds.
This u is the same thing as dx ds. So it's the same u. I'm making the same change of variables here as I did here. So this is the u. Okay? Good. Any others? Yeah.
This question on the middle board where you made the change, where it says 1 over s dv over dx, why is there not a dx over ds next to it?
I have my partial of v with respect to s is equal to, as I have there, it's a partial of whatever I'm doing with respect to x dx ds. And so now when I have this right here, I'm just substituting in here.
And where did the dx over ds?
That is equal to 1 over s. Okay? So ds is 1 over, du or dx ds is 1 over s. And so I put 1 over s here, and that's what I have here. Okay? Good. Any other questions? Good, good, good. Now, all we do is plug and chug. We put it into the equation and see what magic comes out. I'm going to have, from this equation, I'm going to have the partial of v with respect to t, that's fine, plus 1/2 sigma squared. In place of s squared, the partial of v with respect to s, I'm going to have s squared times, what is the second partial of v with respect to s? It's going to equal minus 1 over s squared. The partial of v with respect to x plus 1 over s squared. The second partial of v with respect to x plus, what is the next one? rs. In place of the partial of v with respect to s, I have 1 over s. The partial of v with respect to x minus rv equals 0. Wonderful cancellations. S squared minus 1 over x squared. X 1 over s. So they all cancel very nicely. And so the final equation is going to be, 1 over t, partial with respect to t, plus 1/2 sigma squared, 1/2 sigma squared times the second partial of v with respect to x. That's these two terms right here, cancellation. Now I'm going to have s squared times this, and I'll put it over here. So I'm going to have plus r minus 1/2 sigma squared, the partial of v with respect to s, minus rv equals 0. Okay, everybody with me on that? Yeah. No, just checking out. Okay. Notice where the extra term comes in with the partial of v with respect to x. It comes from the second derivative. It comes from the second derivative. Now, and this is going to crop up again later today. Look at this term right here. We have to expect that the solution to the Black-Scholes should have this term. So when it crops up, don't be surprised. When it crops up, do not be surprised. You're going to see that in about 30 minutes, maybe sooner. Yeah.
I was going to do the partial with respect to x.
Ah, you're right, because I got rid of the s's, so this should be the partial with respect to x. And that makes it better. Any other corrections or comments? Okay, so when you see that term, r minus 1/2 sigma squared, you know where it came from. It came from the s squared term of the Black-Scholes equation. You're also going to see r plus 1/2 sigma squared. And that's going to come from the fact of the variance of delta s by adding it to this term right here. I now have a constant coefficient problem, which should be easier to solve than the Black-Scholes equation. Not quite. Still too many terms. And I want to turn it into the heat equation. So one of the exercises that I gave you for today is to make the change of variables tau equals minus t. And that means that d tau is equal to minus dt. Question? And so when I make the change of variables, what this equation will then become is, it'll just be this right here. The partial of v with respect to tau is equal to 1/2 sigma squared second partial of v with respect to x squared plus r minus 1/2 sigma squared the partial of v with respect to x minus rv. In other words, I'll just get a minus over here. The partial of v with respect to t is going to be the partial of v with respect to tau times the how fast does tau change with respect to t, that's a minus 1. So we just move it on the other side. Okay, any questions? Well, one is, where in the heck are we going? Well, we're going to the heat equation. Now, I'm not going to go through the next term. It'll be in the notes, but I'm not going to go through the next term. There are ways to get rid of these. To get rid of these terms right here. Much like what you had in high school, completing the square. Remember, you had 6x squared. 6x, no, thank you. I'm full. 6x, no, you're trying to sweeten me up. 6x squared plus 10x, and you had to complete the square or something like that. And by completing the square type tricks, we can make this into something that looks like the following. Into something that looks like the following. The partial of u with respect to tau equals the partial, let's make that w, is the partial of w with respect to x. In other words, I have to change v a little bit to get rid of those terms. And the exact steps will be in the notes that I'll give you tomorrow. I'll be sending out tomorrow. Still have to make some corrections. Okay. Now, what have we gained here? What we have gained here is that's the heat equation. And in every 9th grade course on partial differential equations, all right, junior level course at Northwestern, or wrong university, that was where I used to be, at UCI, in partial differential equations, you get the solution to the heat equation. And the heat equation involves exponential minus x squared over 2 from the normal distribution. And so therefore we know, and I'm going to write down the solution, we know that the solution is going to have the normal distribution in it. Will have the normal distribution. It will have the normal distribution. And it will have terms like r minus sigma squared over 2 and r plus sigma squared over 2. So let me describe the technical details are in the notes, but let me just describe the progression. What we did is we looked at the central limit theorem. We looked at the central limit theorem to be able to talk in terms of what should be we use the central limit theorem to say what should be the random term. Think of the assumptions that we had to make, because in the central limit theorem, I'm saying that the way he approaches the market is a random fluctuation. What she does, what he does, what he does, what she does, he, she, etc. In our use of the central limit theorem, we have to have what? Independent. What he does and she does might be independent, but those three of those, they're just munching on candy and they're sharing it, so therefore they're not independent, okay? And so they're not independent at all, but I'm assuming that. Identically distributed, his and his distributions are not going to be the same. And hers is going to be very different, okay? And so what we have is we're making assumptions that we know are not going to be completely true, but what the heck, seems to come out anyway. For mathematicians in the room, that is that is a challenge. What other assumptions will give you permission to use the normal distribution? Can you relax it? And so what we're able to do is we're able to replace the random term with sigma s delta x, where delta x is normally distributed with variance delta t. Next term is y that delta t, and we showed with the use of Ito's lemma, if we don't have delta t, you don't have common sense. Your model doesn't have common sense. Once we have Ito's lemma with a little arbitrage arguments, we have the Black-Scholes equation. But notice all along the way there's various assumptions, and you should be aware of what those assumptions are. Because if the market is really violating those assumptions, be leery of using the Black-Scholes. Next. What we did is we took the Black-Scholes equation and we made changes of variables to get to the heat equation. So we have the Black-Scholes equation. We go through changes of variables. What are they? They're the kind right here. Get rid of the constant coefficients, or variable coefficients. Change the time so that you have everything on the same side. And change v so I can get these terms, rid of these terms right here. That's all it is. And you get this right here. Now, we take the solution for the heat equation, so I have the solution for the heat equation, and we take the change of variables, just those change of variables that we used, to get the solution for Black-Scholes. Remember, the solution to the Black-Scholes is going to depend on the boundary conditions that we computed last time. The boundary conditions are going to give me different boundary conditions on the heat equation. And so that's going to determine whether, it's going to be blow torches on both ends or what it's going to be. And that'll come from there. Okay? And so now, let me give you the solution. So there's the Black-Scholes equation, and I'm going to let V equal C E S T. So I'm going to give you the solution of the Black-Scholes equation for a call. Remember how we started this? We started it with V minus alpha S. And the V minus alpha S was to try to find the value of the option relative to what's going on with the current value of the asset, S. Then we set it equal to R, how much you could get in the bank. And what is that? That gave us information in terms of how is my asset and the option and the asset doing relative to the market. So all that information is embedded in here. And the solution is going to be well, we know that it should have something to do with S and E. Have a lot of space in your notes between S and E because we're going to throw a lot of stuff in between there. Because we know S minus E has something to do with happens at time capital T, at the expiration time, right? Well, before the expiration time, we should look at the present value of T. Well, now we've got to modify it a bit by all the information we got from the market and all the information we have from adjustments, etc. So that's going to be, and it has to have something to do with the normal distribution, and indeed it does. It is the normal distribution up to value D1. And this is modified by the normal distribution up to D2. And what are these terms? Remember, N, D is equal to 1 over root 2 pi, the integral from minus infinity to D of E to the minus x squared over 2 dx. So if I tell you D1 and D2, we're done. We can go out to the market and become rich. Or maybe not. So I'm going to tell you what D1 and D2 are. Well, what do we think we should have? We know from the change of variables that have been going on here, we know a natural log probably should show up inside there somewhere. A change of variable to get rid of S and some of these other type things. So we know a change of variables probably involves the natural log, and it does. It is the natural log of S over E. plus here we come to a term that we expect, r plus 1/2 sigma squared t minus t. And remember when we worked on finding the value of S with the log normal distribution? And we found that delta S, we ended up with S being, the natural log of S being, having the variance sigma squared T minus T, capital T minus T. So therefore the standard deviation for the natural log of S is going to be sigma root T minus T. So that's going to be the first part of the term. Any questions on this? I'm actually 5 minutes ahead. Any questions? Yeah.
R and 1/2 sigma squared, is that plus or minus?
Yeah, all right. That's plus, and I'll write it down. I'll clear this up and make it clear. R plus 1/2. So it's a natural log. So in other words, what happens is when we were talking in terms of the value of S, what we did is we found the natural log of S had a normal distribution, didn't it? And so what we have is that the D1 on here is the natural log of S, which is what we get from the value of S, divided by E. So how much is it above or below E? Then here we have the R plus 1/2 sigma squared T minus T, and that's really coming from change of variables that we have through here. And then D2 is equal to almost the same thing. Natural log again, because this tells you the natural log of E, current value of money, plus R minus 1/2 sigma squared T minus T, all divided by sigma root T minus T. And so it has a large amount of the terms that we should expect to be in there. We computed, by use of Ito's lemma, about what will be the value of S at any given time. And we found that the value of S is the natural log of S is normally distributed. Natural log shows up right inside there, because for D1, it's the natural log of S over E, and the normal distribution is right over here. We get this term right here. This term right here, this is just coming from change of variables type arguments, and we divide by the variance. The variance was sigma squared T minus T, so therefore the standard deviation is this. And D2 is this term right here. Now, yeah, any questions? Now I'm going to ask you questions. First one is, who gives a darn? Who cares? You got this ugly equation. What am I going to get out of it? You have a portfolio. Okay? And your portfolio is and you want to adjust your portfolio. You want to adjust your portfolio, so you want to know what is the, just like in the betting, What is the ratio between the value of the call and how much you should go long, short, or the ratio between the value of the asset? What is the alpha? Remember, what did we find alpha should be? It should be the partial of C with respect to S. And what's the partial of C with respect to S in this equation? Is it? Actually, it's not. The partial of C, only where C is in there explicitly, but it's going to be really ND1. Okay? And so really, if you use ND1, you have a pretty darn good take on what's going to be the partial. What's going to be how you should make your adjustments between them. You got a couple of other S's in there, but when you carry out the detail for the first take, that's what you got. Okay? Let me ask you the following. Suppose sigma, the variance, now I look at the market and wow, it's getting really, really wild, shooting all over the place. What does that mean about sigma? What is sigma? The variance of how the price and everything is going to go. And so if sigma gets large, I mean, give you the answer. All right. So if it's very volatile, sigma gets large. All right. If sigma gets large, the question I'm asking you is to determine what happens to the price of the call. So compute that. Let sigma go to infinity. Let's go really wild. That'll give you some intuition. Suppose sigma gets very, very large. What's going to happen? Pardon?
It's going to get smaller.
Okay. She's saying, look at this. If sigma gets very, very large, this is getting large. So that's going to, what's going to happen to this term? This term right here is going to go to 0. What's going to happen to this term right here? It's going to go to infinity. So therefore, ND1 is going to infinity. And what's ND at infinity? 1. So therefore, this term right here is going to 1. What's happening to D2? D2 is going to minus infinity. Let's take a look. If sigma becomes incredibly large, this term right here goes to 0. This term goes to 0. This term right here, it becomes essentially minus sigma. Minus sigma is going to infinity. So D2 is going to minus infinity. And so what we have is that ND2 is minus infinity to minus infinity, which is 0. And so we have that if the market is really, really getting volatile, if it's really getting volatile, then what you're going to have is that the value of the call is going to be approaching the value of the asset. Okay, any questions on that? Next, suppose sigma is going to 0. Suppose the market is, not much is happening. There's not even a little, you see that line and not even a little wiggle. So what's happening to sigma? Sigma is going to 0 if the market is very, very stable. no variance, no wiggling. So look at the extreme and tell me what's going to happen as sigma goes to 0.
Value of the cos going to be 0, right?
I don't know. I don't know. Sigma is going to 0. Sigma is going to 0. So what happens if sigma goes to 0? Really what I'm looking at is d1, which is the natural log of s over e plus r minus sigma squared t minus t minus sigma squared t minus t over sigma root t minus t over sigma root t minus t. Okay, and what we have, as sigma gets small, what happens to this term? Yeah, this term disappears, it goes to 0. What happens to the other term? Pardon?
Goes to infinity.
Or it goes either to infinity or minus infinity, depending if the numerator is positive or negative. So if the numerator is positive, so if it's positive, then this term will go to infinity. This term will go to infinity. If it goes to infinity, what happens is this term is going to turn to s. And if this is negative, and if it's negative, D1 goes to 0. Yeah? Okay, so he says, I can't make sense out of this. What does this mean? So let's take the natural log of s over t, e, and let's suppose it is greater than minus r t minus t. How do I get rid of the natural log? I take e to both sides, and I will have s is greater than e to the minus r t minus t. So we're asking, is the current value of the stock, sigma is going to 0. Sigma is going to 0, so the market is not really moving. And I'm asking, is the value of the stock larger or smaller than the present value of E dollars? And that will make a difference in terms of the value of the call. Because in that case, this term right here will go to 1 in one case, it'll go to 0 in another case. Now we look at D2. At D2, this term is going to go to 0, and this term right here will either go to 1, infinity, or 0, again, depending on whether the present value of S is larger than or smaller than, whether S is larger than or smaller than the present value of E. So if they both go to infinity, this is going to be the difference between S and the present value of money. If they both go to 0, it's going to go to 0. Okay, everybody with me on that? This is important because the Blac-Scholes equations and the solution of the Blac-Scholes equation are important in the market. And of importance, it's that whenever you're looking at these type of things, the equation itself, you don't have time to look it up. When you're looking at some of the things at the mark, picking up the page, and someone says, what do you think is going to happen? Let me get out my calculator and computers and find my notes. You don't have time. So you develop, this is to develop intuition about what's going on. What we have is that if sigma is getting small, that is the market is going like just before Christmas or something, then what happens is, what's the value of the call? Sigma is getting small. What happens is this gives me the present value of money. And so what I do is it's either going to, if it's greater than that, it's going to be the difference between S and E times the present value of E, or it's going to be approaching 0, one or the other. So you have intuition on this. Question?
So is this thing analysis work for T?
So let's try that. Let's try small t going to capital T. In other words, it's just a couple of minutes before expiration time. So go ahead, figure out what's going to happen. Okay, so let's take a look at D1. D1, and we see that the denominator is going to go to 0, which is why he asked that question. So we just put divide it into into different terms. All right, and so I have natural log of S over E plus R minus 1/2 sigma squared square root of T minus T over sigma. Right? Just dividing out the T minus, no I don't. No I don't. I have that over sigma, and I have sigma root T minus T over here. There we go. Everybody with me on that? And what we have then is, as T goes to T, this is going to 0, so that approach is getting closer and closer to 0. this term right here, as it goes to 0, whether this term is going to either go to plus infinity or minus infinity. Either plus infinity or minus infinity. And the difference depends on whether S is greater than E or smaller than E. Yeah?
So on that board, did you mean to say D1 goes to negative infinity?
I beg your pardon?
Did you mean to say D1 goes to negative infinity or goes
Oh, it goes to negative infinity. I'm sorry. Yeah. Thank you. I was thinking of n of D1. And n of D1 goes to 0, not D1. Thank you. Okay, and so I have this right here. And so this will either be approaching 1 or 0. And then what do I have here? Here I have exactly the same thing. This term right here is going to go to 0. This term right here is either going to go to 1 or infinity. 1 or minus infinity. Yes?
So how about sigma over there? If sigma is minus, it's negative, then it
Sigma can't be negative.
can be negative.
No, remember sigma is the positive square root of sigma squared, of the variance.
Yeah.
So sigma is always positive. Okay? Good question though. And so what we have then is, if this is true, then this goes to infinity, d2 goes to infinity, d2 goes to minus infinity. So what happens then, if we're very close to the time, this, if S is greater than E, this is going to be approaching S. That'll be approaching 1, so this will approach S. This will be approaching 1, so it's going to be really the difference between S minus E. If S is less than E, it's going to be approaching 0. So what happens here, and this is the power of the Black-Scholes equation, is it tells you if you know today's sigma value, R value, etc., you can compute what should be the value of your call. Even better, you can use this equation to develop intuition. When you open up the business page and you say, wow, what happens is we got a gold medal in the Olympics last night. That's really going to affect the stock market. Maybe not, okay? But what happens is, if it does, if sigma gets large, it's going to be a volatile market. You have an idea from the type of arguments we've been using what's going to happen to the value of the call. If it's going to really quiet the market, you have an idea what's going to happen to the value of a call. If the interest rates go up tomorrow, you just play the same game and you have what's going to happen to the value of a call. If it goes down, you again have that information. So what I will be stressing is I'm not going to give you D1 or D2, you know it. You see it, you know it. But what I'm going to be stressing on quizzes, on tests, is what happens if. What happens if S goes to infinity? What happens if sigma goes to infinity or goes to 0? What happens if R goes to infinity or to 0? We look at the extreme cases because they're easier to compute. What happens if T approaches capital T? What happens if, with all of the variables that are here, we got the variables S, E, R, sigma, T minus T. So you have all of those variables to play with to try to determine what's going on. Okay?
this will only tell you what it should be today, since you only know sigma, but sigma can change. over
Sigma
time.
can change, yeah.
So you would, if you just use this equation without looking at anything else.
That's
you
correct.
wouldn't
In
predict-
fact, what happens is a lot of the people on the market, what they do is they get a printout for today. They get a printout for today, what to think if with this particular asset and everything else like this. If S does this, and then here's what you have to expect for your call and your put. They get a computer printout. Where it comes from, they have no idea. It comes from here. But he's asking another question. It's that throughout we've been assuming that sigma and mu are constant. Are they? Not at all. You look at the market. You know they're not constants. And so you get a different equation if you throw in different variables. Second thing is, how do you compute sigma? Well, if you have a very, very good idea, don't tell anyone else in the class, just go to one of the top firms and become rich. Because they hire people to try to determine new ways to find sigma, to find all of these other variables. Because if they know it, they have a competitive advantage. And so that's what we have here. Okay. Let me ask you, we haven't only one more variable to play games with, and that's R. Suppose R goes to 0. Suppose all of a sudden, as we've seen recently, the value of R, interest rate, goes to 0. If you notice from the notes, I had to change numbers from 10% for R down to 2%. So to compute what happens if R goes to 0. Not too much, huh? Not too much goes on. If R goes to 0, what happens is the D1 is going to be determined by this. That's going to be 0. And that's going to be, and we have this right here. So you're going to have a little bit symmetry on there, but not much. If R goes to infinity, what's going to happen? So R goes to infinity, what happens? What's D1 going to do when R goes to infinity? Huh? Well, take a look. Look at that equation. Suppose R gets very, very large. Everything else is the same. What's going to happen to D1? It's going to go to infinity. And what's n of D1 going to go to? 1. And what's D2 going to do?
1, 2.
It'll go to 1, 2. The D2 will go to infinity. So if R, as she argues correctly, if R goes to infinity, this term is going to dominate, and D1 is going to go to infinity. As R goes to infinity, D2 is going to go to infinity. If that's the case, then this is going to be approaching 1. That's going to be approaching 1. And the value of, for high interest rates, we have to expect that the value of the call is going to be the difference between the current price, asset price, and the expected present value of E. Okay? Yeah?
But if R goes to infinity, wouldn't E go to infinity?
0.
Yeah.
Yeah. So it'll be to the current price of S. So he's pointing out that if R goes to infinity, there's another variable in here. If R goes to infinity, this term right here is going to 0. So it'll be approaching S. Very good. Any others? Okay. You've already done almost all of your homework that I'm going to be assigning you. You just have to carry it out now on your own paper. But if you've been taking notes and watching your homework, you can enjoy the sun this weekend. Okay? Except for the last problem that I'm going to assign. Oh, darn. Okay. We know the value of a call. You compute what? The value of a put. Go ahead, start on that, and we'll give you a head start on that. Because that's one of your homework assignments is going to be to find the equation for this right here. Yeah.
What happens if they, instead of the bank giving you interest, they start charging negative interest? They're talking,
Tell me where that bank is.
they're starting to talk about it.
Yeah, I know. That's money. That's doles going out. These equations won't apply.
Because they're starting to charge if you start saving money in a bank.
Yeah.
They charge you.
Yeah. So what happened? But these rates right here are not the same as for what you get. These are the rates that corporations and
Right.
big dealers get.
So they just wouldn't apply anymore?
They don't apply because it applies only for negative, for positive values of R, the Black-Scholes. Okay, so go ahead, try to find what's the value of a put while I get rid of some of the magic here. How would you do this? How would you start this? Anybody got an idea how you would start this? Yeah, a couple of you have said it. Put, call, parity, equation. Write down the put, call, parity, equation. Write down what you have for C, plug, chug, turn the heavy crank. There's about one trick in there. One trick in there, because you're going to have integral going the wrong way. One trick in there, but that's all. So what I'm going to do is something that I normally never do. And that is 10 minutes early, I'm going to say, let's go and enjoy the sun. Now, 6 o'clock to 7 o'clock, I am in some room. You all got the note. I don't know where it is. Do anybody know where that room is? Neither do I. So you have to look it up. And I got to look it up, and I'll be there from 6 till 7 to answer any questions you have. Remember, 2 weeks from today, you have our exam number 2. You know it's going to cover a lot of material. Go and enjoy the sun and start preparing. Oh, be sure you're in study. Who's not in the study group? Who's not in a study group? Everybody in a study group? All right, good. You need to be in your study groups from now on.